Hello students, today we are going to see an interesting and important topic, that is theory of coordination complex compound. By observing that coordination complex compound through electrical conductivity and chemical activity, physical and chemical properties, isomerism. So all this observed, and Werner has brought some statements and related ideas about that coordination complex compound. So that statement only I would like to bring it to you all. So in this session, Werner's theory of coordination complex compound, what are the merits and the demerits of Werner's theory, VBT theory and crystal field theory. This also let us go and observe. Come on. First one, Werner's theory. So Werner has brought that theory. So generally, coordination complex compound means two things will be available. Two point, it is very, very important. One, it is central metal ion. The other one, it is ligand. Ligand, it is sharing the pair of electron to the central metal ion. So now here, coordination complex compound of metal ion. The first point, coordination complex compound of metal ion, has divided into two main points. First one, it is a primary valency. Second one, it is a secondary valency. Primary valencies are ionizable, secondary valencies are non-ionizable. What do you mean by ionizable? That is ionizable equal to its oxidation state. That is number of electron lost by its central metal atom or ion. That is, it has to be satisfied by negative ions. So please remember, negative ions means that is belongs to primary valency. Okay, now what about secondary valency? Secondary valency, already I mentioned what it is, non-ionizable. This has to be satisfied by negative ions and neutral molecules having lone pair of electron. So example here, halogen, cyanide, ammonia, water. Ammonia, water, it's a neutral. Halogen and cyanide, it is a negative ions. Okay, now the second point, what it has mentioned, only 3 points. The second point is number of secondary valencies of metal ion or atom is fixed. That is equal to its coordination number. Now, for that, what is the example? Here, 6. Suppose coordination number 6. Example, that is platinum 4 plus, iron 3 plus, chromium 3 plus means that coordination number will be 6. Whereas 4 means palladium 2 plus, platinum 2 plus, Cu 2 plus, Ni 2 plus. These are all coordination number 4. And whereas 2, coordination number 2 means here Cu plus, Ag plus, Au plus. These are all coordination number 2. Then the last point, the ions, a group bounded by the secondary linkages, the linkage between that ligand and the central metal atom, right? So the secondary linkages to the metal have characteristic spatial arrangement of the respective to their coordination number. So 4 means it is a secondary valency, that is tetrahedral shape. So that they are giving that, providing the spatial arrangement, that is shape of the molecules also. Right. Now 6 means 6 of that secondary valency, it is octahedral. Okay, now let us go and identify what are the molecules. How can we identify? What are the merits? What are the demerits? Let us go and observe. Now, these are the points about the statement one who has brought. Who has brought that? Alfred Werner has brought that. What it is? Well, coordination complex compound theory. Okay, now let us go and observe that example, merits and demerits of this theory. According to Werner's theory, let us go and observe one example. In that, let us go and identify different properties of that compound. Okay, first and foremost, cobalt 3 chloride and ammonia complex. Okay, let us go and identify the different properties. First and foremost, let us go and see COCl3 6 NH3, COCl3 5 NH3, COCl3 4 NH3. In that, compounds, colors, moles of AgCl PPT. AgCl, why do we take it? Because it's a chloride compound. Okay, let us go and observe with that. And solution conductivity corresponding, because electrical conductivity. Let us go and observe. And Werner's formulation. Okay, now first and foremost, COCl3 6NH3. What is the formulation of Werner's? CO NH3 6 times 3Cl, and here 3 plus actually. Okay, so this is ligand and coordination number, central metal ion, coordination sphere, oxidation number, and oxidation state, and this is ionizable. Yes. Okay, let us go and check that color. This is yellowish color and precipitate with AgCl. Number of moles here 3. Okay, now solution conductivity corresponding 1:3 electrolyte. Okay, here some of the demerits also available. Which is primary ion, which is secondary ion, he did not mention clearly. Okay, so that is actually demerits. Let us go and check with the demerits that time. Okay, now the second one here, purple color. This is COCl3 5NH3. Now formulation what it is? CONH3 and 5 times, and this is what it is. Here also 3 plus, and here what it is? 3Cl. Okay, now this is purple color, and number of moles with the PPT AgCl here 2 moles, and here 1:2 electrolyte. And the third one here COCl3 4NH3 means here green color. Green color the same way here CONH3 4 times 3Cl here 3 plus. Right? Now here in this, here 1 mole of AgCl with PPT you will get it in this, and here 1:1 electrolyte. Okay, so in that way we can identify all these examples. Okay, now let us go and identify what are the merits and demerits of Werner's theory. Now let us go and analyze merits and demerits of Werner's theory. Okay, merits in that point, what it has mentioned, formation of complex ion. It explains that Werner's theory explains the formation of complex ion, geometry of complex ion, and differentiating between primary and secondary valencies. Whereas demerits are which will be adoptable for that VBT theory. Okay, now what are the demerits we can identify from this Werner's theory? First and foremost, it does not explain that offer electronic interpretation of complex ion. Electronic configuration we could not provide it very clearly in this, and how ligand can satisfy primary and secondary valencies of central metal ion, and why only few elements possesses the remarkable properties of forming coordination compounds, and why the bonds of coordination compounds directional property, and the last one, why these compounds have magnetic and optical property. For these questions which could not answer for Werner's theory, so these are all answerable in VBT theory. Let us go and check VBT theory next point. Now let us go and analyze that VBT theory given by Linus Pauling. Okay, he has given some assumption of VBT theory of coordination complex compound. First and foremost, coordination complex compounds are two main points, that is metal ion and ligand. Metal ion acts as a Lewis acid because it accepts electron, whereas ligand acts as a Lewis base because it is donating electron. Yes. Now, in the next assumption, coordination complex compound contain metal ions. Ligand has lone pair of electron. Metal has that, what it is, central metal ion has an empty orbital of suitable energy for bonding. Now, the next point, atomic orbitals are used for bonding, and that is useful for predicting shapes, stability of metal complexes. So, what are the demerits means? It does not explain why some of the complexes are colored. The second one, the temperature depends on the magnetic property. Why the temperature depends on the magnetic property? He did not explain. So, now we are going to analyze some important from VBT. Okay, first and foremost, COF6 3 minus, that is coordination complex compound. So you have to find out hybridization, geometry, that is shapes of the molecule, magnetic property, inner or outer spin, and lower or higher complexes. These are all you have to find out as you look at that compound only. Okay, now as we have gone through that assumption, now I'll give some ideas, that is a tricks for you to identify. First and foremost, coordination complex compound, that coordination complex compound, first and foremost you have to find out the oxidation number of that. Okay, oxidation number whom you have to find out for the central metal atom or ion. So find out oxidation number. Okay, find out oxidation number for what? Central metal atom or ion. The second one, identify whether it is a weak field ligand or strong field ligand. Okay, ligand and metal ion combined together only coordination complex compound. Okay, now identify weak field ligand or strong field ligand. Okay, weak field ligand and strong field ligand. So, weak field ligand means cannot pair up the electrons in that atomic orbitals. Okay, cannot pair up the electrons. Okay, that means strong field ligands means can pair up the electrons. That is the main point. Okay, now how to identify weak field and strong field? Example I would like to give you. It is F minus, Cl minus, such kind of ions and are weak field ligand. And strong field ligand, for example, NH3 and Cn minus, these are all strong field ligand. Okay, now, what is the purpose I mentioned, can pair up, cannot pair up in the electronic configuration of the atomic orbitals. Okay, now let us go and identify with these points. Now, first and foremost, you have to identify what it is. Find out the oxidation number. COF6 3 minus. Now, how to identify the oxidation number? This is X plus 1 into minus 6 equal to minus 3. So, X minus 6 equal to minus 3. So, X equal to plus 3 oxidation state. Now, the second one, here in this point you have to identify whether it is a weak field ligand, strong field ligand. Of course, this is F, it is there, so it is a weak field ligand, cannot pair up. Okay, now let us go and identify with this electronic configuration. CO, atomic number how much? 27. So 27 means 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. Right? So this is the atomic electronic configuration. Okay. Now let us write shortly argon 3d7, 4s2. Okay. Now in that oxidation state of cobalt, it is 3 plus oxidation state. So we can remove those 3 electrons from the outermost orbital. So that means argon 3d6 4s0, because it is loses what it is, 3 electrons from the outermost orbital. So 3d6 it is available. Okay, now we have to prepare the empty orbitals to receive all the pair of electrons. How many pair of electrons here? How much is there? Here F6. So that means that much we have to keep ready. So that means 3d6, 4s0, 4p0, 4d0. Okay, here how many? 1, 2, 3, 4 and 5. Here 1 s orbital, here 1, 2, 3 orbitals are there. Here 5. 1, 2, 3, 4, 5. Okay, now in this, according to Hunt's rule, electrons will go and fill in that single, then it has to be double. But here we cannot identify like this. This is what it is, coordination complex compound. So here 6 electrons are there now. 1, 2, 3, 4, 5, and here what it is? 6. Okay, now here, come to this point. This is weak field or strong field. This is weak field. Fluoride, it is a weak field. So, fluoride ion, it is a weak field, means it can pair up or it cannot pair up. It cannot pair up. According to that, I have given the clue tricks for you. So, it cannot pair up. Suppose if it is pair up, means these are all, it will go and pair the electrons. But here, fluoride ion, it is there, it cannot pair, it does not adjust with that electron. So naturally unpaired electrons are there. Okay, now here fluoride ion, from where it will go and fill means from here. How many? 1, 2, 3, 4, 5 and 6. Okay, that means here 1, 2, 3, 4, 5 and 6. Here from here to here, this is s orbital, p 3 orbitals, d 2 orbital. So pair of electrons, it will go and accumulate, right? Who is giving that? Fluoride ion. It's donating a pair of electrons to the central metal ion. Which is a central metal ion here? Cobalt. Okay, hope you're clear with it. Now come to this point. What are the points they are asking? Here, hybridization. You got that hybridization? sp3d2. So first and foremost, here, what is the hybridization? sp3d2. Right? Now, magnetic property. Magnetic property, how to identify? If it is unpaired electron, it's a paramagnetic. It's a paired electron, it's a diamagnetic. Okay, I hope you got an idea. It's a unpaired electrons are there. So here, unpaired electron means it is a paramagnetic. Okay, now next one, geometry. What is the geometry? It is octahedral. Octahedral complexes. Okay, now inner or outer, D2. That D2, it is outside, d orbital which is outside. So naturally it is a outer complexes. Outer complexes. And the next one, it is a lower spin or higher spin, means it is a higher spin complexes. Higher spin complexes. Okay, now here also higher spin complexes, we can identify that D2, it is out. Suppose if it is D2 comes here, the here from that fluoride ion which is going to occupy, means we can say it's a inner spin or lower spin, we can say. Okay, now Bohr magneton, how to identify the Bohr magneton? Bm is equal to root of what it is? N into n plus 2. Okay, n it is what it is? Number of unpaired electrons. N it is what it is? Number of unpaired electron. So how many unpaired electrons are there? 1, 2, 3, 4. So 4, 4 plus 2. How many? According to that, you have to calculate it. So here, root of 4 into 4 plus 2. Unpaired electrons, how many? According to that, we have to calculate. It is root of 24. They may ask the question, root of 24 of Bohr magneton. How much is that unpaired electron? In that way also they may ask. Okay, hope you're clear with this idea, how to find out the hybridization, geometry, magnetic property, inner and outer spin. So such kind of thing, I hope you got a clear idea. Through the trick, you can identify all this. This is 3 mark or 4 mark question they will ask. Hope you're clear. Okay, let us go and identify some more coordination complexes compound. Now the next question, FeCN6, 3 minus. Find out the hybridization, magnetic property, geometry, inner and outer complexes. lower or higher spin? Find out this. Okay, first and foremost, what we have to do, find out the oxidation number of this complex. Then we have to check whether it is a weak field ligand, strong field ligand. Why? It has to pair or unpair. Okay, then next one we have to go for the electronic configuration to identify. Yes, the first one, what it is? FeCN6 3 minus. Okay, now oxidation number we have to find out. Okay, so this is X plus, this is Cn minus, right? So 6 into minus 1 is equal to minus 3. So X minus 6 equal to minus 3. So naturally X equal to plus 3, oxidation state. Now atomic number of Fe ion, it is 26, right? Is that equal to 26? Okay, now electronic configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6, right? So this is 10 and 10, yeah, 26. This is 26 now. Okay, now how can we write it another way? That is Ar, that is argon, 3d6, 4s2. Okay, now this is iron. This is actually what it is. Fe3 plus, right? Fe3 plus. So leave 3 electrons from the outermost orbital. So we can write it Ar, 3d5, 4s0. Okay, now how to, we have to prepare for that empty orbitals to fill that ligands, right? So we can write 3d5, 4s0, 4p0 and 4d0. Okay, let us draw the atomic orbitals. 1, 2, 3, 4, 5, and this is 1 and this is 3. 1, 2, 3p orbital and here 5. 1, 2, 3, 4 and 5. Okay, now here, now we have to check whether it is a weak field or strong field. Cn, it is a strong field. Already I just mentioned that in the trick. Okay, so according to that strong field, it can pair up or cannot pair up. It can pair up the electrons, right? So that means here 5 electrons means 1, 2, 3. That means 1, 2, 3, 4, 5. So this is empty orbital. So empty orbitals, it is preparing for what? To fill the ligands. That means a pair of electrons received from the ligand to that. Who's that receiving electrons? Central metal ion. Which is the central metal ion? Ion, it is a central metal ion. Okay, so that means here Cn and here Cn. How many ligands are there? 6. Cn and 1, 2, 3. Cn, Cn. 1, 2, 3, 4, 5, 6. Okay, so it will fill here. So 1, 2, 3, 4, 5 and 6. So now we have to find out what are those points. Hybridization, magnetic property, geometry. Okay, now in this point, hybridization, what it is, first and foremost, this is D2sp3. So here what it is, hybridization, D2sp3. Now magnetic property, is there any unpaired electrons are available? Yes, of course, only one unpaired electrons are there. So if I put it different way, you can identify. So these are all what it is, ligand filled. So this is what it is, unpaired electron. So only one unpaired electron. So here what it is, paramagnetic. Paramagnetic. Next one, geometry. This is octahedral complexes. Octahedral complexes. See, naturally, if it is 4 comes means tetrahedral or square planar. Whereas here, octahedral comes, that is 6 and above comes means it is octahedral. Okay, now the next one, Bohr magneton. Bm is equal to root of n into n plus 2. So how many lone pair of electron? That is only one, right? Here unpaired electron 1. So 1 into 1 plus 2. So how many? Here 3 only, right? So it is paramagnetic in nature. Hope you're clear with that. All inner and outer complexes or higher spin or lower spin. So D2 comes in the front only. So naturally what it is? Lower spin complexes. Inner spin and lower spin. We can mention what it is. Here inner complexes and lower complexes. Hope you're clear with that. Okay, now we'll go for this. Is actually 3 mark or 4 mark. Definitely you may get some questions such kind of this. Hope you're clear with it. Okay, we'll go some more examples. The next one more interesting question. NiCl42 minus, find out hybridization, magnetic property, geometry, and so on. So, okay, this coordination complex compound, first and foremost, we have to find out the oxidation number. So, what is the oxidation number? How to find out? So, nickel, it's a central metal ion, and chloride, it is a ligand. So, chlorido, it is X, central metal ion plus 4 into minus 1 equal to minus 2. So, x minus 4 equal to minus 2. So, x equal to plus 2 oxidation state. Right. Now, next one, electronic configuration we have to write. So, nickel atomic number it is 28. And we have to write it electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. Right? You got it? 28. Now, we can write it in this way. AR 4s2, 3d8. Now, this nickel, how much it is oxidation state? 2 plus. So, that means we have to remove 2 electrons from that outermost orbital. So, AR 3d8, 4s0. Right? Now finished this one. Next step what it is? We have to prepare empty orbitals to fill the ligands, right? So for that, the same idea we have to follow. Empty orbitals 1, 2, 3, 4, 5, and this is 1 and this is 3 and this is 5. 1, 2, 3, 4, 5. Yes. Now the next one. Electrons it has to fill now. How much electrons it has to fill? 8, no? So that means whether it is a weak ligand or strong ligand, here you see Cl minus, it is a weak ligand. So it cannot pair up the electrons. So that means here, how many electrons are there? Here outermost 8, right? So 1, 2, 3, 4, 5, 6, 7, 8. So these two it cannot pair up. It is an unpaired electron. So these are all empty. Now it starts. Ligands can start from where it has to. Ligand can start here from here. Cl, here Cl, 1, 2, 3 and 4. So it has to fill here 1, 2, 3 and 4. So altogether how many? sp3 hybridization. So what is the hybridization here? sp3 hybridization. Okay, now magnetic property, as you mentioned here, what it is? Unpaired electron. So what is it? Unpaired electrons? Naturally it is a paramagnetic property. Okay. For the geometry, I would like to give one small trick. According to that coordination number, after that hybridization and geometry. Okay. Coordination number 4. Coordination number 4 means here sp3 d sp2. Right? What is the geometry you can find? Tetrahedral. Okay, sp3 means tetrahedral. Okay, now dsp2 means square planar. Square planar. Right, now the coordination number 5. Coordination number 5 means sp3d. This is sp3d coordination number 5. So here trigonal. Trigonal bipyramidal. Trigonal bipyramidal. Okay, coordination number 6. Here D2sp3 or sp3d2. These both are octahedral. Octahedral complexes. Okay, hope you're clear with this idea. If it is so, where do you identify the hybridization? According to this, you can identify the hybridization. Then, if it is like this, now you can identify what is this sp3, what it is belongs to. It is tetrahedral. Tetrahedral. Okay, hope you're clear. Okay, BM, what is it? Unpaired electron. How many unpaired electrons are there? Root of n into n plus 2, right? So, it is 2 into 2 plus 2. Hope you're clear with it. Now, this is the way we can find all these ideas. This is actually 4-mark question. Easy way to analyze all these points. Okay, now next session we are going to see some more examples of VBT theory as well as crystal field theory, which is very, very important. Hope you understand all these points. Thanks for watching. Please subscribe this channel so that you will get all the notification. And one more thing, if there is any doubt, please put it in your comment box so that I can answer. Thanks for watching.